Well, good afternoon and Happy New Year. My name is Dwayne Brown from the Office of Communications. Welcome to NASA headquarters. Today, you will hear about NASA's upcoming Valentine's Day rendezvous with a comet. We'll have brief presentations, and then we will open it up for questions. So let's get started. First, let me introduce you to today's participants. First up will be Joe Ververka, Stardust Next Principal Investigator, Cornell University, Ithaca, New York. Tim Larson, Stardust Next Project Manager from Jet Propulsion Laboratory, Pasadena, California. Pete Schultz, Stardust Next Co-Investigator, Brown University, Providence, Rhode Island. And Steve Chesley, Stardust Next co-investigator, also from the Jet Propulsion Laboratory. So with that, I'll turn it over to Joe.
Thank you, Dwayne. Good afternoon. We are here to update you on the Stardust Next mission, which is less than a month away from its encounter with Comet Tempel 1 on February 14th. And it's important to realize that Stardust Next involves the reuse of a spacecraft. As the next slide shows us, we are hoping to see the next slide. Okay, all right. As I mentioned, Stardust Next reuses the Stardust spacecraft, which was originally launched in 1999. The goal of this original Stardust mission, next step, was to visit Comet Bill 2. Let's see where, thank you. And the idea was to fly by Comet Bill 2 and collect dust in a capsule and return that capsule with the dust to Earth for analysis. That was done successfully 2 years later. Next step, please. The capsule with the sample was returned to Earth in January 2006. And since then, these samples have been analyzed in laboratories around the world. Next step. And they continue to provide important information about how comets were formed and about the earliest processes in the solar system. So Stardust itself was a great success. And the thing to remember was that not only was it a great success, but it left a perfectly working spacecraft out in space. And so the next step shows us that in 2006, we decided to ask NASA to send this spacecraft, to reuse it, and send it on another mission of exploration. The target, the next step, please, Comet Tempel 1, that's the comet that was visited by Deep Impact in 2005. So why go back to Tempel 1? Well, there are two answers. One is that Tempel 1 turned out to be unusually interesting. The next slide shows us that in places on Tempel 1, we see layered terrains, which probably contain information about how comet nuclei were put together. And we would like to see more of these terrains. Deep Impact saw only about a third of the surface. We would like to see more. And as the next slide shows us, we would also like to see more of the areas that Deep Impact saw, these smooth flows, which apparently suggest that comet nuclei are not only modified by processes from the outside, but also by internal processes. So there are things that we would like to find out about Tempel, which we don't know at this time. But the next time step shows us probably the most important reason for going back to Tempel 1, and that is that this will be an opportunity for the first time to see how much a comet changes between two close passages to the sun. Deep Impact saw the comet in 2005. We'll be seeing it one comet year later, just after its closest passage to the sun in 2011. So the question is, we know that comets lose material, but the question is, how much does the surface change and where does the surface change? So we'll be able to answer that question by comparing our images with those taken by Deep Impact in 2005. So to achieve these two objectives, we have a definite plan. It's summarized in the next time step, which shows us a surface map of Tempel 1. The gray mosaic shows us data that were obtained by Deep Impact in 2005. The yellow area, yellowish area, is the projected new coverage on Valentine's Day. As you can see, there is a region of overlap where we can be looking for changes, and there is a region where we're looking at new territory that was not seen by deep impact to extend our knowledge of the comet. Now, you also will notice that there is a bullseye in the middle of this diagram, and that is the location where deep impact in 2005 excavated a crater. And the next time step reminds us that that impact threw up so much ejecta that deep impact never saw the crater. So it could never complete the experiment of seeing how big the crater is and what that tells us about the mechanical properties of the comet surface. That's important if we're ever going to go back to a comet, land a spacecraft on the surface, dig up material from the surface to bring it back to the Earth. We need to know something about mechanical properties. So here, we have a chance to complete the deep impact experiment. So to achieve all of these things, as will be described in a few minutes, we have chosen an encounter time where we can do these two things that we want to do. And we have chosen a mist distance of 120 miles from the surface of the comet. Shown in the next time step are some of the images that we expect to take right at closest approach. Not only will we be taking 72 high-resolution images, we'll also be collecting information on the amount and the type of dust that surrounds the comet. And these measurements will be described in a little bit more detail by later speakers. Let me just say that the resolution that we expect to achieve, about 12 meters per pixel at best, is sufficient to address all of the objectives that I've discussed. In the last time step, just want to remind us that we are getting closer and closer to the comet every day. The spacecraft is working wonderfully well. The spacecraft team is working hard preparing all the data-taking sequences that we'll be using on Valentine's Day. The navigation team is working very hard to make sure that we get to where we need to be on Valentine's Day. And all I can say about the science team is that the science team is awfully excited and just cannot wait to see the pictures and the dust data that we expect on Valentine's Day. And with that, I'd like to turn it over to our project manager, Tim Larson, who will give us a few more details about the mission itself.
Thank you, Joe. We've mentioned already the Stardust Next is a bonus mission, and it takes advantage of some key factors. One, we have a spacecraft that's still working well after being in space for almost 12 years now since launch. It's traveled almost 6 billion kilometers since launch, so it's got some mileage on it, but it's still working well, able to do another mission. We also have a scientifically desirable target, or an interesting target, that we can get close to with the fuel that we have left. And most importantly, we have a team of people that has the skills and innovation and the dedication needed to pull out this kind of a mission. We have people that have been flying the spacecraft at Lockheed Martin in Denver, Colorado, since the time it was launched. So some wonderful, dedicated people that know the spacecraft inside and out, know how to make it do what we need it to do, and that's what really enables this mission. As you may recall, this is the second comet encounter for NASA in the last 4 months. The Deep Impact spacecraft flew by Comet Hartley 2 in this last November. That was a great success. But like comets are all different, also comet missions and flybys are all very different and have their own unique sets of challenges. So let's talk about our spacecraft first for a little bit and some of the features of the spacecraft and some of the challenges that we're dealing with here. You'll see a scale model here of the Stardust spacecraft. You'll see at the top of the spacecraft are the solar arrays that generate the electric power that we use to power the spacecraft and to operate all the equipment on board. Also on the top, you will see this larger antenna. That's our high-gain antenna, part of our radio system that we use to communicate with Earth, and that's what enables us to get the higher data rates to be able to get all this data back down to Earth. And then you'll see these bumpers at the very front here and in the front of the spacecraft body itself. These are the shields. This spacecraft was originally designed as a comet flyby spacecraft, and these shields were designed and put in place to protect the spacecraft as it flew through the coma of the comet and to protect it from dust particles impacting the spacecraft. At that time, at 6 kilometers per second, this current next flyby will be at a speed of a little over 10 kilometers per second. And so these shields are what provide our main protection for the spacecraft. Now, in terms of instruments that will be gathering data as we fly by the comet, if you look at this side of the spacecraft, you'll see this feature right here. That is the navigation camera with its mirrors and periscope that is able to look out past the shields as we approach the comet. And then on the other side of the spacecraft, you'll see another instrument that comes down with its sensor sticking down below. Again, that's another sensor that's out in the flow of the dust. This is the Comet and Interstellar Dust Analyzer instrument that will help us characterize the dust environment that we fly through. And then the third instrument is mounted right in the circle that you see at the front of the spacecraft, and that's the dust flux monitor that will further help us characterize the dust field that we fly through. So these are some of the key features of the spacecraft that has done so well for us over the years. As mentioned earlier, this spacecraft is repurposed. We've recycled it, and it's had a whole entire life. And I'd like to show you with the first animation that you'll see here. It'll show you a little synopsis of the life of this spacecraft, starting with the launch in 1999, February of 1999. So this spacecraft is coming up on 12 years in space. It's had a long and illustrious life, well beyond its original planned design life, but it's still working well. Since its launch, it traveled halfway out to Jupiter and back. It executed a flyby of asteroid Anne Frank, and it also executed then the flyby of Comet Vil 2. After that flyby, where it collected the dust samples, it returned that capsule back to Earth, creating a large fireball as it came through the atmosphere. It was the fastest man-made object to re-enter the Earth's atmosphere, and it's the first time that we've been able to return samples from outer space back to Earth. After that flyby, the spacecraft continued, circling the Sun, and now we've been able to retarget it to meet up with Comet Tempel 1. And after all of that, it still has some fuel in the tank. But that's one of the challenges that we're working with here, is the remaining fuel and managing the remaining fuel. With the way we design our spacecraft and our missions, we account for all kinds of uncertainties and unknowns, and that's why we usually have some fuel left after our primary missions, and that's what enables these kinds of extended missions. However, the challenge is to make sure that that fuel lasts as long as you need it to. Everything we do on the spacecraft consumes fuel. It is a spacecraft that's controlled strictly by reaction control thrusters, and so every time we turn the spacecraft, every time we point the spacecraft, our daily just dead banding as we control the attitude of the spacecraft, all of that consumes fuel, and so we have to predict all of that into the future, predict everything we're planning on doing with the spacecraft, calculating how much fuel that's going to consume, and making sure that we have enough and we control our activities to make sure we have enough fuel to make it through the flyby and playing all those images back to Earth. So that's been one of our biggest challenges, and it's one that we pay very close attention to, and I'm happy to tell you that we really are confident in having enough fuel to finish up this mission. Although after this mission, there won't be much left that this spacecraft can do. In the process of retargeting the spacecraft and taking it over to Comet Tempel 1, we conducted 3 additional orbits around the Sun. We conducted 5 targeting maneuvers, and the largest one of those maneuvers was one that we executed last February. Now that maneuver was a special maneuver for us because a year before getting to our target, we had to decide when we wanted to arrive at the target within the matter of several hours. And that was our best opportunity to change that arrival time. If we had waited until we have seen the comet, or as we get close to the comet, say for example now, we would have very little adjustability left. We'd be able to adjust our arrival time by maybe an hour at most. So we had the ability, if we did the burn a year before getting to the target, was one of our best times we had the best lever arm in our trajectory to be able to adjust our arrival time. That's when we had our best shot at doing that. So we had to make our best predictions, and Steve's going to talk to you a little bit about that process of predicting what phase of the comet we expect to see when we get there. And based on those predicts, is how we chose our arrival time burn. This was a 23-minute burn of our rocket engines, and it delayed our arrival at the comet by about 8 or 8.5 hours. And so that was a major event for us almost a year ago, last February. So now as we get closer to the comet, we'll start getting busier and busier. A lot of the activities that take place can only take place once we get very close and have the knowledge that we need to be able to design these appropriately. So our last targeting maneuver as we approach the comet is 2 days out. That is the last maneuver that will be fully designed to target to our 200-kilometer flyby distance, and that will be executed 2 days before we arrive at the comet. Right after that maneuver, we'll be taking our last optical navigation images, and those are the images that we'll use to build our best prediction of our actual flyby point and the path of the trajectory of the comet relative to the spacecraft. Once we build that, then we will load up at 24 hours out. We'll load up our final sequences that have been built with that latest estimate estimate of the time of closest approach, and that final data on the comet trajectory will also be loaded onto the spacecraft. And from then on, the spacecraft will be working autonomously. We cannot control the spacecraft real time, and here's another challenge with this mission. The spacecraft is currently basically opposite the sun from the Earth, so we're about 2 astronomical units away from Earth at the time of encounter. That means when we send a comet up to the, or command up to the spacecraft and wait for the confirmation that that command arrived there and was executed properly, that round-trip light time is approximately 40 minutes. So there's nothing we can do to command the spacecraft or control it real time during a flyby like this. Therefore, everything has to be programmed ahead of time, put on board the spacecraft and sequenced, and everything happens autonomously on board the spacecraft. So 1 hour before we get to the comet, the spacecraft will turn to orient itself with these shields facing forward to protect itself as it flies through the coma of the comet. About 30 minutes before closest approach, our AutoNav software will activate, and that's essentially an autopilot software on board the spacecraft that analyzes the pictures that we're taking of the comet, figures out where the brightest spot is, calculates that as being the center of the nucleus, and then adjusts the position of the camera mirror so that we can keep the nucleus in the field of view of the camera all the way through the flyby of the comet. Then if you'll roll the second animation, this will show you what we expect to see as we fly by the comet and the kind of images we expect to get of the comet as we fly by if everything goes as planned. This is assuming a 200-kilometer flyby, about 20 degrees south of the sun line, and if the phase of the comet is as we predicted. And so it's exciting to see this kind of information coming out and see these kind of simulations that show us what we expect to see on February 14th as we fly by. As we fly by, our closest approach will be about 8:30 in the evening Pacific time on Valentine's Day, February 14th. In the few minutes around closest approach, we'll be taking the bulk of our images. We'll be taking 72 high-resolution images. We cannot transmit those to the ground real time because of the flyby geometry, so we have to store all of those on board in the spacecraft memory. An hour after the flyby, we turn the spacecraft to point the high-gain antenna back at the Earth, and at that point, we'll start relaying all this information back to Earth, and that'll take approximately 12 hours to get all this data back down on the ground. Our first images should be hitting the ground around midnight Pacific time on the evening of the 14th. So that's what to expect during our flyby and some of the key things that will be happening. And to talk to us a little bit more about what we might see when we get there and the geology of the comet, I'd like to introduce Pete Schultz.
Thanks, Tim. Deep Impact was really a groundbreaking mission with many firsts. Groundbreaking also by the impact probe that actually produced a brand new impact on the nucleus. So the first time, we're going to be going back and we'll actually get to see what's happened since the time we were there. Now, the Earth has been around the sun 5.5 times since our last visit. The comet has been all the way out to near the orbit of Jupiter, back in just inside the orbit of Mars, and now it's heading back again. And during this time, the comet has had several outbursts. One of them happened about 10 days before our close visit by the Deep Impact spacecraft. So in 2005, we saw a surface with a wide range of features, some old, some new. And if we go to that first time step, I'll give you some examples. This is a color rendition done by the Deep Impact science team that shows you some of the different types of terrains, which I'll be discussing in a little bit more detail. But you can see that there's these hilly areas, smooth areas, areas that look like they're layered. But if we go to the next time step, we can take a look at this in more detail. The top image shows the raw surface without any markings. On the lower part, I've identified some of the interesting areas. One of them are the crater-like features. The first reaction is that these might be impact craters, but they may not be. These could be sites of ancient vents where gases were erupted. This may have been millions of comet years ago, and now they're just sitting there extinct. There are other areas like that, the little blue regions that are these knobs, these dark knobs. And the dark knobs are poking up through a layer that we can actually identify. And then the other white circles, or the yellow arrows identify small white patches that could be ice, could be mini jets that are coming out this old surface. And the most interesting thing is this large plateau that looks like a flow. And if that's a flow, it was indicating that there was gas and dust emanating out from the left-hand side off the terminator edge and then flowing into the region toward the center. But the other idea is that maybe this was there beforehand and this was just an old accumulation of being around the sun several times, and now it's simply receding backwards. So the real point is that now with going back, we'll be able to take a look at the surface and actually see what's changed. Has this gotten longer? Has it gotten more forward, or has it moved backwards? So the next time step, we look at the two ends of the comet. Here we can actually see, again, a smooth deposit or flow, and we can also see a bright deposit right next to a pit. Now, that bright deposit turns out to have been water ice. The Deep Impact Science Team members discovered that with the spectrometers. But the other thing I want to point out are the layers that Joe mentioned. One idea, these were two proto-cometary bodies that collided at very low speeds and smushed together the comet to form like a stack of pancakes. And that's what we see left. We don't know if that exists all the way around the side, so there's going to be something to be looking for. At the bottom, you see the knobby terrain at the other end of the comet. So what we can see out of this is that this surface, this comet, has really a complicated geologic history. It's not just a fuzzball. It has history. And so by going back, we can see how it's been changed. And we can look at other features that we've yet to see on the other side. So as has been mentioned, it may be difficult to see the crater. So give you an idea, let's go back and take a look, an example, the next time step, at a couple craters. Now, in this case, this is a crater of the moon. On the moon, it's an oblique impact. On the left, there's an image of the moon from high sun angle, so the sun's right overhead, and the other one is where the sun is off to the right, which casts this shadow. So what you can tell is that you can tell this is a crater, you can tell it's oblique. Let's go to the next time step. Now we've degraded this down to about 10 meters per pixel. This is a little bit better than what we'll see with the closest approach by Stardust Next. The next one is around 25 meters, next time step, 25 meters per pixel. This is probably going to be what we'll get. If we're lucky, problem, not a problem, measuring the crater diameter or the ejecta if we're on that side. And then finally, if we keep going to 50 meters per pixel and then 75 meters per pixel, you can tell that we're beginning to lose resolution, and that may be the case if we don't come in on the side that we expect. So regardless, I think if we see the ejecta, we should be able to see the crater, and we might be able to measure it. So the real point about this is that even though these things are from a great distance, because this will be going at a slightly, even though it's closer, the cameras are not the same cameras that we have for deep impact, we should be able to resolve the impact. Now, what happens if we see the crater and there's no ejecta? Well, one possibility is that the ejecta was thrown out, it was icy stuff, and all that ice is sublimated away, evaporated away. The other possibility, it hit and formed a dark halo, because there was a dark layer that we saw there. So we're dealing with a lot of unknowns here, and we're hoping we'll be able to get back to see it. So this particular encounter is going to answer a lot of very fundamental questions. And I really hope we get to see this impact crater, but that's going to be a bonus. Everything depends on how that nucleus of the comet has rotated around. And with that, I'll hand it over to Steve Tesley.
Thanks, Pete. So as Tim mentioned, about a year ago, the Stardust Next spacecraft executed a timing maneuver. It's the biggest maneuver of the follow-on mission, and it was a culmination of a massive undertaking to try and model and predict the spin state, the rotational orientation of the comet, so that we could meet the mission's primary objectives and hopefully get a glance at the crater. We can go ahead and start the animation, please. So comets are comets because of the gas and dust that they emit as the ices on their surface cook off when they approach the sun at the closest approach to the sun we call perihelion. Here's a video, highly processed, showing the jets that are rotating, especially on the right. You can see they turn on, they turn off, they spin around. That video is from the epoxy flyby of Hartley 2. But the point here is that comets are not just inert, simple objects floating out in space. They're dynamic, they're active, they're much more like a rocket with no one at the controls than something that's just idling there. And these unpredictable jets can change not only the comet's rotation, but also its orbital path through the solar system. And this is the reason why the comet dynamics can be so complex, even erratic in some cases. And And so for this reason, it is a challenge to target a spacecraft to a flyby or rendezvous with the comet. In our particular case, the challenge is a bit higher because we haven't even seen this comet up until a couple of weeks ago. We saw it last in June of 2010, just as it was starting to become active, and we were not able to monitor its progression as it became active and passed through perihelion about last week. Until a few weeks ago, Bill Ryan at Magdalena Ridge Observatory in New Mexico was able to image it in the dawn twilight, only about 25 degrees from the sun and on the other side of the sun. And we were all very pleased to see that it was right about where we had predicted it to be. And that's finding the Tempel 1 close to the prediction is important because it suggests that this time around through the sun, while we weren't able to monitor it, it has behaved more or less as it has in previous passages, and there's no rule that says comets have to do that. And that's important for our mission because our fuel budget is tight, and it would be unfortunate to be forced to expend a lot of fuel trying to make a large course correction to get lined up with the comet because it had decided to take a crazy turn. Also, seeing it behave predictably is reassuring for our efforts to model the rotation of the comet. And that's, as I mentioned, was a huge effort that we wanted to achieve the mission objectives, which is to put, basically put the high-dollar real estate in sunlight facing the spacecraft at the flyby. And hopefully, as a bonus, get a glimpse of that crater. So this was a worldwide effort. The next slide is up, and you can see that the observing side of this campaign comprised dozens of telescopes around the globe, many dozens of observers. This was a massive observation campaign led by Karen Meach at the University of Hawaii. And as a result, it's safe to say that Tempel 1 is the best observed comet in the catalog. These observations have been accumulating over more than a decade now. What I have here is a model of the Tempel 1 nucleus. You can see the North Pole is here, South Pole is here, and the deep impact crater is just here, deep in the southern hemisphere, and it rotates like so, and it puts the broadside to the observer sometimes, at which point it's bright, or it puts the skinny end towards the observer, so it's a little bit dimmer. You can go to the next slide, and you can see what happens, what the observer sees at this, as this forms a light curve. If we can get the next slide, please. These are a series of points, in this case taken from the Hubble Space Telescope, that show it brightening and dimming as we see these alternate ends of this comet. And our objective is to take this data. I should mention that this is the Hubble Space Telescope data for ground-based observing, which comprised the bulk of the data we used. We don't get to see a full revolution, as is shown here. We see maybe 10 or 15% of one rotation period in a given night. But the point is to take this model of the comet and combine it with these data. Next slide, please. And you can see how we try and line these things up. But the alignment is imperfect because the model that we have is imperfect, coming from the Deep Impact mission, and we didn't see all the way around the comet surface. Next slide. So we use this to line things up and measure the speed and estimate the alignment of the comet. But as you can see, next slide, there's two. There's a primary solution that you're looking at here, and there's an alternate solution on the next slide. And from a variety of perspectives, we're very confident that we have chosen the right orientation. But comets, being the unruly beasts that they can be, there is always a chance that this opposite phase correlation is the right one. Well, to reach these conclusions, we had two independent groups using different but very complementary analysis techniques. Mike Belton led what we call the Tucson group, and I led a group at JPL. And after more than a year of intense effort, lots and lots of cross-checking, we reached the same conclusion, that Tempel 1 is accelerating. Every time it passes through the close approach to the sun, it gets a little boost in its rotation speed. We could even see that acceleration in the light curve that came from the Deep Impact spacecraft all by itself. And the shared conclusion went further. We actually have a very detailed model of the jet-induced torques that the comet is experiencing. We see a very strong and brief acceleration around the time of perihelion, but in the background, there's a much weaker deceleration that operates for a much longer time period. So Tempel 1 is the first comet to have such a detailed and precisely measured and modeled rotation. And of course, this was originally a scientific objective, but eventually the Stardust Next mission needed to know the orientation of the comet, and so it became a mission objective as well. So if we have aligned our light curves correctly, and if the comet continues to cooperate as opposed to deviating radically from its previous behavior, then we will meet our mission objectives on February 14th, and hopefully also have a fantastic view of the deep impact crater. But the alternative is not so bad, because then we'll get a fantastic views of never before seen cometary terrain. So we'll have fantastic science no matter what. There is the question of will we see the crater, or will it be camera shy? And we won't know until a few hours after the flyby. I'll be on the edge of my seat, but I think it's important to emphasize that that aspect of the mission is bonus science, and we're going to find out a lot about how comets evolve from perihelion passage to perihelion passage come February 14th. With that, I'll pass it back to Dwayne Brown.
Okay, well, thank you, gentlemen. We're going to now go to the phones, and before we do that, I have a couple of questions from some of the .coms that are on the line here. Probably for you, Joe, to start off. Why is it important, and summarize this in layman's terms as you can, to study comets? And if what we know now, how is Stardust Next going to change the knowledge and data?
Well, generally, the idea is that comets preserve some of the most faithful information about what happened when the solar system formed. And we do know that comets do contain interesting molecules, some of which could have been involved in the origin of life on the Earth. So the overall objective of comet studies is to get to the point where we can actually return sizable samples of cometary material to do a chemical analysis which will answer the question whether we are comet stuff or not. Now, what is the role of Stardust Next? Well, we are not going to be returning samples, but for example, by imaging the crater, if we're successful, we will learn more about the mechanical properties of the surface. So when there is a next mission that tries to land on the surface, there'll be data on how difficult it will be to remove a sample from the subsurface to bring back to Earth to answer these questions. So it's a step towards the ultimate answer.
Anyone else want to chime in on that? No. Got it? The next question, this is actually for each one of you, and I'm going to start at the opposite end with Steve. They want to know your personal thoughts on the success so far of the spacecraft, and what are your possible expectations and excitement building personally. So, Steve, we'll start with you.
Well, that's a great question. I mean, the Stardust spacecraft has been around the block, as we've heard many times, and so it's pretty exciting to see something keep on getting reused and producing bonus science at every turn. For me personally, I've been closely involved with the trajectory analysis for this comet, and so I'm hoping to see it be close to where I predicted when we finally get there. And I also have been working hard on the rotation modeling. So I've kind of got two irons in the fire here, and I'm excited to see whether or not the things pan out for the predictions.
Pete?
You know, I think, you know, as we said, I mean, all of us have said, we want to see what this surface has done. It may be a very different place. There are some structures that have to have been around for a long while, but it's these other features that we want to see. Of course, I want to see the impact crater. Bets are in. I want to find out if I win the pool. And that's my hope. Personally, I want to see the crater. But I'll take the other option to see the other side.
In terms of expectations for this flyby, I'm very confident in our ability to get there. We have a great navigation team at JPL that's working hard to make sure we get to the right place at the right time. I've been working closely with the spacecraft team at Lockheed Martin in Denver now for the last 2.5 years or so, and I'm very confident in the ability of this team to do everything that needs to be done to make the spacecraft do what it's supposed to do. And we've assessed all our major uncertainties or challenges. We've addressed all of them. So I'm frankly very, very confident in the results of that we're going to get a good flyby and good images of the comet. On a personal note, though, I think I would also, to me, it's going to be a great follow-up to previous comet missions I've been involved with. Started out with Deep Impact and the Tempel 1 flyby in 2005, following that up with the Hartley 2 flyby this last November, and now an opportunity to go back to Tempel 1. For me, it's a huge excitement, and every time we've pulled one of these missions off, new discoveries have come out of them, and so I expect this to yield some new discoveries for us, no matter what side of the comet we see.
Joe, final thoughts?
Well, I guess 2 points. One is I just want to emphasize that we know very little about how comets behave. And we saw some images today where Peter Schultz showed us different features on the surface. We have no idea how fast any of these features change. Are some of them, millions of years old, or some of them 2 years old? And so I think the thing that we're looking for is to start answering that question. Okay. The second thing I wanted to say was that I think it is extremely rewarding to be able to look forward to accomplishing first-rate science with a spacecraft that's already done wonderful things, that has used up most of its fuel, and managing all those resources to achieve great science. And I think that's very rewarding to all of us.
Well, gentlemen, we have a number of folks on the phone, but I believe you guys' presentations were so airtight, you answered all the questions. So what I'm going to do here is wrap it up. I want to thank folks for joining us. Of course, if you want additional information about this incredible mission of spacecraft, go to www.nasa.gov. Also, on a programming note, tomorrow at 1 p.m. Eastern Time here at NASA headquarters will be a media briefing about the agency's next Earth-observing satellite mission called Glory. It's scheduled to launch on February 23rd. And panelists will discuss the spacecraft's mission to study the impact of the sun and airborne particles on Earth's climate. Thank you again. Happy New Year, and congratulations to the team. Thank you.